on continuous and normal random variables. I'm going to start by talking about Twister, or more precisely about any game that has a spinner in it. I want you to think about spinning a spinner, and think of that as a probability experiment, a repeatable process with a different outcome each time. I want to ask you some questions and see if your intuition is enough to answer them. So first of all, what's the probability when you spin this spinner that it lands on one of the feet? You can see the upper left-hand corner and the lower right-hand corner are labeled by the 2 feet. Probability, of course, is 1/2, right? Because half of the circle is labeled left or right foot. How about the probability it will land on red? That's going to be 1/4, because you can see 1/4 of the area is devoted to, or of the length of the circle is devoted to each of the 4 colors. A little bit trickier. What's the probability of getting within 1 degree of that top black line? Of course, within 1 degree means anywhere from -1 degree to +1 degree. Or 1 out of 180. Why? Because the whole circle is made up of 360 degrees, so the probability of landing on one of 2 of them is 2 out of 360. But it's not just made out of 360 degrees, it's made out of 360 million millionths of a degree. So what's the probability that you get within 1 millionth of a degree of that line? It's going to be 2 out of 360 million. It's going to be a tiny number. What's the probability the arrow will point exactly on the vertical? Well, it's got to be less than 1 out of 180. It's got to be less than 1 out of 180 million. But it's also got to be less than 1 out of 180 billion, right? That's the probability it's within a billionth of a degree. It has to be 0. But on the other hand, it can't be 0, because if it's 0, every point on the circle has probability 0 of being picked, and then how does any point ever get picked? There's something completely unintuitive about this, the continuum of possibilities in this on the circle that this spinner represents. But on the other hand, when I asked you questions about ranges of values, it was easy. You knew exactly the chance of getting landing on a foot or landing on red. That problem, which is obviously not very practical since there isn't a whole lot of deep statistics in Twister, but that problem is exactly the same problem that you have to deal with any time you deal with a continuous random variable, like the time it takes you to run a mile. It makes sense to ask, if I go out and run a mile, what's the chance I'll make it between 8 and 9 minutes? That's a reasonable question you can answer if you sort of had data from your past few hundred runs. But it doesn't make sense to ask what's the probability of running exactly 9 minutes. Or if it does make sense, it would have to be 0. So we need a trick that allows us to talk about the probability of a range of values for a continuous distribution without ever talking about the probability of individual values. It's a kind of strange idea, but there's a trick, it works brilliantly, and to see it, we need to think about histograms. So let's think about the histogram of one continuous random variable, which is women's heights. When you make a histogram, you have to choose a bin size. So let's choose bins of 4 inches. Well, if you choose bins of 4 inches, you find that most women fall in one of these 4 bins with their tiny, tiny bins out here. You can't really see. And it looks sort of bell-shaped, high in the middle, with tails on either side, but pretty crudely bell-shaped. If you have a lot of data, you might as well have a smaller bin size, maybe 1 inch. And now it looks much better, right? Bin sizes of 1 inch, you start to see that characteristic bell shape. It still looks pretty jagged, but overall you get a bell shape. If we did 1/4 of an inch, if we had a really big data set, we could look at a histogram with 1/4 inch bins, and it would look like this, and that's really starting to look like a nice smooth curve with tiny little wobbles in it. So let's imagine, sort of philosophical point, imagine taking a limit as we get more and more bins, that distribution gets more and more like a smooth function. And of course, implicitly, when we drew pictures of the shape of distributions, we drew continuous functions like this to represent the shape, because we didn't want to think about the bin size and the wiggles. We wanted to think about the shape. So we want to think about the underlying continuous function as being the limit of this histogram getting finer and finer, and is really representing the continuous random variable. So we're going to represent continuous random variables by continuous functions, f of x, right? That's the graph of a continuous function. And we're going to, just like ordinary probability distributions, you had requirements that the probability of each value has to be between 0 and 1, they have to add up to 1. We're going to require that the probability is never negative, has to be between 0 and infinity, and the area under the curve must be 1. Why is that? Because now we're going to represent the probability that x falls in a certain range of values by the area under that curve in that interval. Right? So for example, that shaded area above represents the probability that a random woman's height will fall between 60 and 66 inches. The probability x is between 60 and 66 is represented by the area under the curve between 60 and 66. That should have a tingle of familiarity. You've talked about the area under the graph of a function f of x between x equals a and x equals b before, and you probably even remember the name you gave it. It's the integral. Okay, so the integral of f of x from a to b gives you the probability that the random variable will fall between a and b. Probability that a randomly selected woman's height will be between a and b. And here's the really, really important point. That integral tells you something about the probability, but the function itself doesn't. The value of f of x at x doesn't tell you anything. In particular, it's not the probability of the woman's height being exactly x, because that's 0 for each x. So in general, you can have any function at all. We will not deal with general functions. I'm going to give you one example in the examples, the optional examples lecture. But I won't hold you responsible for integrals of anything except the one very important example. We'll have one family of examples of continuous distributions, or the only one we'll consider. It's called the normal distribution. We've said before that many random variables you find in nature are roughly bell-shaped. Even more, they have a sort of standard and recognizable bell-shaped distribution. They all look pretty similar. There's deep mathematical reasons for this, which we will learn. But those mathematical reasons point to one special function f of x that is the standard bell-shaped distribution that anything you see in nature that's bell-shaped is, let's say, trying to approximate. That special function is called the normal distribution, or the Gaussian distribution, named after our friend Gauss. There is one normal distribution for each mean and standard deviation, so we can think of it as depending on mu and sigma. How are we going to use this in practice? When you meet a random variable in nature and you see or believe that it is symmetric and unimodal, and you know its mean and standard deviation, then you can model it by the normal distribution with that mean and standard deviation. You can use calculations with the normal distribution to approximate probabilities of this naturally occurring random variable, whose probabilities you will generally not know exactly. I'm going to introduce you a little bit to the beauties and wonders of this amazing function, and then I'll show you how to calculate with it. The beauties and wonders might be a little intimidating. They are not the exact formulas you're seeing here will not be important to the calculation. There is the formula for the normal distribution with mean mu and standard deviation sigma. It's a pretty complicated formula. Let's take it in pieces. First off, up in the exponent, you see x minus mu over sigma, which is exactly the z-score. And that's the only place x shows up. So this distribution only depends on the z-score. The normal distribution only cares about your z-score. Out front, you see a big mess that involves, of all things, the square root of 2 pi. That mess out front is only there because, remember, the integral of the function from minus infinity to infinity, the total area under the curve has to equal 1, that number is stuck in there to make it equal 1. That fact that the integral of the stuff that isn't red from minus infinity to infinity equals 1 over the stuff that's red is a beautiful calculation that I'm sad to say we don't have the time or wherewithal to go through, but it's quite remarkable that this square root of 2 pi comes up out of nowhere. The base of the exponent is e. Again, e you remember from calculus. Irrational, 2.71828, etc. It's the result of $1 spending a year at 100% interest compounded continuously, and it's the natural base for exponents. And it's quite magical that e and pi and square roots and other highfalutin mathematical stuff show up in this naturally occurring statistical phenomena. Here's what the graph looks like. Well, there's a different one for each mu and sigma, so there are a lot of different graphs. But here are a few examples. The blue graph has a mean of 0, so you can see it's centered at x equals 0, that's where its peak is, and a standard deviation of 0.2. So it's tall and thin, whereas the red one has a mean of 0, same mean, but a bigger standard deviation. It's shorter and fatter, right? Standard deviation means more spread out. Since the total area has to be 1, that means it has to be shorter. The yellow is even shorter and fatter because it's a mean of 0 and a standard deviation of 5. And the green has a mean of negative 2. So it's centered at negative 2 and its standard deviation is a middling 0.5. So if you move the mean around, if you move mu, the curve shifts to the left and right. If you change sigma, the curve stretches or contracts. One last point about the mathematics of this. If you go up and down from the mean, of course the mean is the maximum, the high point. If you go up and down from the mean one standard deviation to here and to here, that you know underneath the area underneath that region should be about 2/3 by the empirical rule. But another interesting fact about those 2 points, mean plus or minus a standard deviation, is those are the points where the curve shifts from curving downwards, from concave down, to curving upwards, concave up. If you were sledding down this hill, that'd be the point where you were going the fastest. There's a name for that. Again, from calculus, you may remember, those are inflection points. So the mean is at a critical point, mean plus or minus standard deviation are at inflection points, and calculus seems to be all over the place here. So as we said, the probability that a normal random variable will fall between a and b is going to be the integral from a to b of this normal distribution. That looks like a scary thing to integrate, and you are right to be afraid, because not only don't you or I know how to integrate it, you can prove that there is no formula whose derivative is this function f of x. So none of the clever techniques that you learned in calculus to find an integral exactly will work here. That's actually not a problem, because it's actually pretty easy to do integrals numerically. That is, to approximate the area under the curve as closely as you'd like. It's the kind of thing that's a pain by hand, but that Excel or any computer is perfectly happy to do, and in fact Excel has a built-in function for approximating that integral. So we will probably never write another integral sign for the rest of the course, even though we'll spend all semester integrating normal functions. Excel's command is called normdist. So if you want to compute probability for a normal distribution with a mean mu and a standard deviation in sigma in Excel, you use the command normdist. The probability that that random variable is less than or equal to a number x is equal to normdist of x, comma, mu, comma, sigma, comma, 1, where x, the first entry, is the number you're comparing it to. You're going to get the probability of getting less than that number. The second entry is the mean of your of your distribution. The third entry is the standard deviation, sigma, of your distribution. And the fourth entry is always 1. Why does Excel make you write 1 every time you do this calculation? There is no reason. It's just silly. We just have to get used to it. And there's a different command that Excel decided to give the same name that you get if you put a 0 in there, which we'll never need to think about. Just think of it as some ritual invocation of the muse. Alright, so normdist tells you the probability of getting less than or equal to some value. What if you want the probability of getting greater than or equal to some value? Well, that's the complement, right? If you're not less than something, you're greater than it. So the complement is 1 minus the probability of the original event. So to get the probability of being bigger than A, you take 1 minus normdist of A. More often, you'll want the probability of being between two values, A and B. Then you take normdist of the bigger minus normdist of the smaller. I'm only mentioning the first entry because the other three stay the same. They're always the same, mu, sigma, and y. So normdist of big minus normdist of little. That's the one we'll most often use. We'll occasionally use the one-sided ones. What about the probability that x is less than b? That's the same as the probability x is less than or equal to b in a continuous distribution because the probability of being exactly b is 0. So we don't have to worry about that distinction. All right, what do these probabilities look like in practice? Let's do some examples. Women's heights have a bell-shaped distribution with a mean of 65.5 and a standard deviation of 2.5. What's the probability a woman's height will be between 61 and 64 inches? That's a typical normdist question. The first sentence tells you a variable, tells you that it's bell-shaped, or it might tell you that it's symmetric and unimodal, or roughly bell-shaped, anything like that, to indicate you can use the normal distribution, and it should tell you a mean and a standard deviation. Then it asks for a probability. So the probability that x is between 61 and 64 is normdist to the bigger minus normdist to the smaller. So we take normdist 64, comma, the mean, comma, the standard deviation, comma 1, minus normdist of 61, comma mean, comma standard deviation, comma 1. We type this into Excel, equals normdist, etc., minus normdist, etc., and we get 23.8%. I'm going to show you that real quick. In the examples, optional examples lecture, I will do a number of examples, but I'm just going to show you this one. Equals normdist. As soon as you type normdist, you can see it prompts you for x, mean, standard deviation, and 1 it calls cumulative. That'll help you remember. 64 was the upper value, 65.5 was the mean, 2.5, and 1 minus normdist 61, 65.5, 2.5, 1, and we get, sure enough, 23.8. That is, after you do it a few times, not too difficult a calculation, but it's an easy one to mess up. I'm going to show you it's easier to do drawing than on a computer, and I'll show it in class, but I'm going to show you a thing that once you get into the habit of doing is very quick and will catch many, many errors. Because the nice thing about errors on the computer is a little tiny mistake generally causes a dramatic change in the answer. So it's easy to catch if you have an expectation of what's a reasonable value. It can be a pretty crude expectation. So what you do when you're doing a normdist calculation is draw a bell. Okay? You draw a bell and you mark the middle, the top point, with whatever your mean is. In our case, 65.5. You go up and down one standard deviation. How do you tell that? You go roughly where their inflection points are. And you mark those as the mean plus or minus the standard deviation. So in this case, 65.5 minus 2.5 is 63, plus 2.5 is 68. So you mark 63 and 68, maybe you go same distance up and down and mark them 70.5 and 60.5 if you like. And then you look at your two numbers. Where's 64? 64 is right around here. It's pretty far down into that yellowish green. 61 is all the way down here, pretty far down into the red. What's the area that's between them? Well, we know there's about 2/3 in here. We know there's about a 1/6 in the red and the purple. Or I'm sorry, about 1/3 each in the red, in the purple. I'm sorry, 1/3 total. I was looking at these numbers and there's a mistake here. 1/3 total in these two regions. So what's between here? Well, it's certainly less than half. It's not a huge amount less than half. So 23.8 looks reasonable. It's not tiny. It's not more than half. Let's do another example. Between 70 and 73 would be norm dist of 73 minus norm dist of 70. Otherwise, everything's the same. That works out to 3.46%. Let's see if that's reasonable. 70 is, 70 is well into the purple. 73 is quite a bit above that. So it's pretty much just the area of this little white tail here. And that little white tail, because 95% is in the colored region, that white tail is about 2.5%. So it's just a little bit more than that, 3.46%. Okay, as I said, more examples are in the examples video. Occasionally, last thing to learn to compute, you want to go the other way. For example, take the same example, women's heights. Suppose you want to know the 80th percentile. Why do I say that's going the other way? Because you're asking, what's the number, B, such that if I put it into norm dist, I'd get 0.8 out, right? I'm inverting norm dist there. So it's called norm inv, the inverse of norm dist. And you compute it like this. B, that 80th percentile, equals norm inv p, comma, mu, comma, sigma. 3 parameters here, not 4, where B is the value you're looking for, P is the percentile, mu is the mean, sigma is the standard deviation. So in our case, we're looking at norm inv of 0.8, 65.5, 2.5, and that works out to 67.6. So 67.6 is the 80th percentile of women's heights. Last thing to tell you about the normal distribution is to remind you of the empirical rule, right? The empirical rule gave you a rough idea for symmetric unimodal distributions, how much of the data fell within how many standard deviations of the mean. That's really just a crude version of something that the normal distribution tells you exactly. So, for example, in a normal distribution, it isn't quite true that 95% of the data falls within 2 standard deviations. The exact figure is 95% of the data in a normal distribution fall within 1.96 standard deviations of the mean. Okay? That is something we are going to use for the rest of the semester, and you'll just have to remember it. 95% of the data in a normal distribution fall within 1.96 standard deviations of the mean. You can ask that about anything. Instead of 95%, you could ask 99% or 90%, and in general, the answer to that question, how many standard deviations up and down do you have to go to get C of the data, is the number called Z star C. So Z star of 0.95 is 1.96. In Excel, this rather complicated formula will tell you Z star C of anything. I will never ask you to use it. You do not have to remember it. We will occasionally, later on, refer to Z star of 0.9 and Z star of 0.99. Those are important values that you're welcome to just memorize, not too hard. Okay, so after watching this lecture, here is what you should be able to do. You should be able to recognize when a variable can be modeled by the normal distribution, that is, when it's symmetric and unimodal, and you know its mean and standard deviation. You should be able to roughly estimate normal probabilities using the empirical rule. That's good to check your calculations when you do the third thing, which is calculate in Excel the probabilities of a range of values and percentiles for normal distributions. And then after we've worked with this for a while, you will see how all of those calculations are related to z-scores, which is what they're really all about.